How can a single atom be more powerful than a whole cluster? That is the mystery of single atom catalysts. Superactivity, where individual atoms, often metals like platinum, iron, or palladium, serve as exceptionally efficient catalysts, sometimes outperforming much larger particles made of the same material. This seems counterintuitive. Shouldn't more atoms mean more reaction sites and greater activity? Yet in SACs, the exact opposite often occurs. A lone atom, precisely anchored on a support surface, can exhibit unique electronic properties, making it more reactive, selective, and efficient than its multi-atom counterparts. Why is one atom so special? In clusters or nanoparticles, many atoms are buried inside and do not participate directly in reactions, but a single exposed atom has 100% atom efficiency. Every atom is available for catalysis. Moreover, because it is not surrounded by identical neighbors, its electron cloud interacts more strongly with the surrounding support and reactants, often adopting unusual oxidation states or bond geometries. Example, single atom platinum on ceria can catalyze CO oxidation at room temperature, something bulk platinum struggles with. Analogy, it's like a lone genius in a team, unconstrained, hyper-focused, and making bold moves no group consensus would allow. The superactivity of SACs is rewriting the rules of catalysis, opening new frontiers in green chemistry, energy, and nanoengineering, one atom at a time. How can isolated metal atoms, each anchored on a solid support, exhibit catalytic activities and selectivities that far exceed those of nanoparticles or bulk metal surfaces? Single atom catalysts, SACs, present atomically dispersed active sites whose unique electronic and geometric environments can unlock reaction pathways. Yet their exceptional performance raises deep questions about the very nature of catalytic activity. So far, so good, until we probe what makes a lone atom so special compared to clusters of dozens or hundreds of atoms. In SACs, the absence of metal-metal bonds forces every atom into an unsaturated coordination state, intensifying its ability to adsorb and activate reactants, supports such as oxides, carbons, or metal-organic frameworks, donate or withdraw electron density, tuning the atom's d-orbital occupancy and creating charge-polarized sites that stabilize unusual reaction intermediates. These quantum size effects can dramatically lower activation barriers for key steps such as CH cleavage or OO bond formation, yielding turnover frequencies that dwarf those of larger particles. At its core, the paradox hinges on the balance between coordination, unsaturation, and electronic modulation. A single PT atom on CO2, for example, can bind CO more weakly than a PT nanoparticle, preventing poisoning, while still activating O2 efficiently via support-mediated electron transfer. Yet this same undercoordination makes SACs thermodynamically prone to sintering. Without neighboring atoms to anchor them, single atoms can migrate and coalesce under reaction conditions, erasing their superactive character. Yet even this insight conceals further subtleties. The local environment around each atom can differ by just one or two support oxygen vacancies, leading to a spectrum of site types with distinct reactivities. Under working conditions, dynamic restructuring, including reversible oxidation state changes and migration between support sites, can create transient, highly active species whose lifetimes and concentrations are dictated by reaction temperature, gas composition, and support morphology. Capturing this fleeting behavior requires in situ spectroscopy and microkinetic models that integrate quantum calculations with surface diffusion dynamics. At even finer scales, the interplay of ensemble effects and site isolation emerges. In some reactions, pairs of adjacent metal atoms cooperate to form bimetallic active motifs, blurring the line between single atom and cluster catalysts. Meanwhile, long-range support defects can channel reactants toward SAC sites, amplifying local fluxes and creating hotspots of activity. These mesoscale transport phenomena mean that overall catalytic performance reflects not just single-atom chemistry, but the collective architecture of supports and reactor flow. In essence, the single-atom catalyst's superactivity paradox reminds us that reducing a catalyst to its smallest conceivable unit can paradoxically amplify its power, so long as we manage the quantum, surface, and transport factors that sustain it. Much like the slip boundary paradox exposes the breakdown of continuum mechanics at nanoscales, and the quantum vacuum energy extraction paradox underscores conservation limits in exotic settings, SACs challenge us to develop multi-scale frameworks, bridging atomistic theory, operando characterization, and reactor engineering to fully harness their promise. Single-atom catalysts, SACs, consist of individual metal atoms dispersed on supports, achieving turnover frequencies far exceeding those of nanoparticles or bulk metals. This superactivity defies classical scaling laws, which predict that larger ensembles of active sites should proportionally boost overall reactivity. In SACs, every metal atom is a fully exposed active center, eliminating inactive bulk regions and maximizing atom efficiency. The paradox highlights how pushing size to the atomic limit unlocks new catalytic behaviors unattainable in larger clusters. Gold nanoparticles are catalytically inert for CO oxidation at room temperature, whereas isolated Au atoms on Ceria catalyze the same reaction with high activity. It is like replacing a crowd of people shouting directions with a single, perfectly clear megaphone delivering instructions to an entire stadium. Cluster catalysts feature small aggregates of metal atoms where only edge and corner atoms participate in reactions, leaving interior atoms inactive. Single-atom catalysts, by contrast, have no bulk interior. Each atom is an active site in a well-defined coordination environment. Bulk catalysts rely on collective electronic states of many atoms, whereas SACs function as discrete quantum centers. This fundamental distinction explains why classic surface chemistry models fail to predict SAC performance. A platinum nanoparticle of 2 nm diameter contains many subsurface atoms that do not contribute to catalysis, while a PT1 site has 100% of its atoms available. It is like comparing a hidden orchard with many underground roots to a row of fruit trees where every branch is laden with ripe fruit. Quantum confinement in SACs shifts the metal atom's d-band center, altering adsorption strengths for reactants and intermediates. Isolated atoms exhibit unsaturated coordination, creating localized electronic states that enhance charge transfer during rate-limiting steps. These unique electronic fingerprints optimize binding energies according to Sabatier's principle, boosting catalytic turnover. Thus, single atoms access activity peaks that larger clusters cannot reach. Density functional theory shows that a single Fe atom embedded in graphene binds CO more weakly than bulk Fe, reducing poisoning and enhancing CO oxidation. It is like tuning a violin string to the perfect tension so that it resonates louder with each bow stroke than a thicker, less responsive string. Strong metal support interactions, SMSI, anchor isolated atoms via covalent bonding or charge transfer, preventing aggregation while tuning electronic properties. The support modifies the metal's electronic density, creating new reaction pathways and lowering activation barriers. Often the support itself participates in bifunctional catalysis, synergistically enhancing activity. This coupled behavior contrasts with weakly interacting nanoparticles that rely primarily on metal-metal bonding. Single PT atoms on TO2 exhibit enhanced water-gas shift activity because the TO2 lattice donates electrons to the PT center. It is like a perfectly fitting glove that not only secures a tool in place, but also routes extra power to its tip for superior performance. The local coordination geometry and chemical identity of anchoring sites, such as metal-nitrogen-carbon motifs, dictate SAC activity and selectivity. Point defects, heteroatom dopants, or vacancies in the support create specific anchoring pockets that fix the metal's oxidation state and ligand field. Adjusting these features tunes reaction energetics at the atomic level, enabling precise control over product distribution. Defect engineering thus becomes a cornerstone of superactive catalyst design. Single co-atoms coordinated by 4 nitrogen atoms in a carbon matrix, co-N4 sites, show exceptional activity for oxygen reduction in fuel cells. It is like crafting a custom socket that holds a single screw driver bit at the perfect angle, allowing you to drive screws in tight, awkward spots with ease. SACs often exhibit an abrupt increase in turnover frequency once metal loading is low enough to ensure true atomic dispersion. Above this dispersion threshold, atoms begin to cluster, and per-atom activity collapses to nanoparticle-like behavior. The nonlinear transition highlights the emergent nature of SAC superactivity and the critical importance of isolated sites. Even small increases in loading can therefore drastically reduce performance. Plotings above 0.5 bit/% on alumina tend to form PD clusters, after which CO hydrogenation rates per PD atom fall sharply. It is like adding just enough sugar for coffee to taste perfectly sweet, but a little more sugar makes it cloying rather than simply sweeter. The exceptional atom efficiency and tunable activity of SACs promise greener, more cost-efficient catalytic processes. By minimizing precious metal usage, SACs are being developed for key reactions such as CO2 reduction, hydrogen evolution, and selective oxidations with high selectivity. Rational design integrates support selection, defect engineering, and electronic modulation to target specific bond activations. This paradigm enables bespoke catalysts that outperform conventional materials across industry sectors. Single RH atoms on MOF supports catalyze the conversion of syngas to ethanol with high selectivity, a reaction challenging for standard RH nanoparticles. It is like designing a custom key for a single unique lock, ensuring a perfect fit rather than using a generic master key. Characterizing SACs under reaction conditions demands advanced operando techniques such as aberrations-corrected STEM, X-ray absorption, spectroscopy, and Mossbauer spectroscopy to confirm atom isolation and oxidation state. Modeling requires coupling quantum chemical DFT calculations of individual sites with kinetic Monte Carlo simulations of macroscale behavior. Capturing dynamic processes like atom migration and site reconstruction adds further complexity. Overcoming these challenges is essential for predictive catalyst development. Tracking PT1 migration on graphene under CO oxidation conditions reveals site resilience, but also potential for sintering at high temperatures. It is like trying to map the positions of single dancers on a crowded stage in real time while they continually move and interact. Machine learning accelerated multi-scale modeling is rapidly identifying new SAC support combinations with optimal activity and stability. Emerging supports such as two-dimensional materials and metal-organic frameworks offer novel anchoring motifs for atom trapping and electronic tuning. Insights from SACs are informing broader theories of heterogeneous catalysis, potentially unifying disparate reaction mechanisms. Ultimately, mastering single-atom superactivity promises transformative advances in energy conversion, environmental remediation, and fine chemical manufacturing. AI-driven screening has pinpointed EAR1 sites on silicon carbide that rival platinum for hydrogen evolution activity, while requiring 100-fold less metal. Is like using a drone fleet and AI to survey vast landscapes for the perfect microhabitats to introduce rare beneficial plants, achieving ecosystem restoration with minimal resource use.